Greetings, AP Stat students, and yes, I started this video the same way that I start all my videos. So today we're going to be looking at we're still looking at section 12.2, which is transforming to achieve linearity. We're looking at transforming relationships in order to achieve a linear relationship. Our goal is to fit a linear relationship to data that may not necessarily be in a linear relationship with one another. But if we transform them by manipulating a little bit of the values of one variable or both variables, we can turn them into a potential linear relationship. So what we're looking at today is transforming with logarithms. Specifically, we're going to be looking at exponential models. So we did power models previously. Now we're going to be looking at exponential models. Exponential models, x is going to be your power, whereas with power models, x was your base. So sometimes the relationship between y and x is based on repeated multiplication by a constant factor. That is, each time x increases by 1 unit, the value of y is multiplied by b. An exponential model of the form y equals a times b to the x describes such a multiplicative growth. Okay, so as I increase x by 1, this will become, if I start with x being 1, this is a times b. But if I increase x by 1 to 2, now it's a times b squared. Then it's a times b cubed, a times b to the 4th, a times b to the 5th, so on and so forth. So you're, as you increase x by 1, you are multiplying what y results in by another factor of b. Okay. So here's our exponential model, y equals a times b to the x. Now the crucial property of logarithm for our purposes is that if a variable grows exponentially, its logarithm grows linearly. So keep this in mind as we go through this right here. We're going to take the log of both sides. So we're, in this case, just do base 10. It really doesn't matter what base you use. But we take the log of both sides of this exponential model. Now, this is not something that you'll necessarily have to do. So we're just showing you how this works. How does it come out to be a linear relationship here? Well, because of our properties of logarithms, we can break this product, a times b to the x, down as separate logarithms and add them, a sum of logs. So log a plus log b to the x. And because of our power property that x can come down in front of log b, and so we get log y equals log a plus x log b. Okay. Now, when we did power models, I just want to point this out. So this just shows you that we come up with a linear relationship here. This looks an awful lot like y equals a plus bx, even though there's logs in there. Now, when we did power models, we had to take the log of both variables to turn the resulting relationship into a linear relationship. With this one, we'll only have to do log of one variable or the other. Typically, the log of the y, not necessarily the log of the x, because nowhere in this do we take the log of x in this. We're doing the log of y. So we will typically take the log of the y variable to transform the relationship. So looking at an example, Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are the data dates and the number of transistors for Intel microprocessors. So you've got microprocessors from 1971 all the way to 2010 here, and the number of transistors on those. Okay. So this figure 12.17 shows this right down here. Let me move this down so we don't have that in the way. It shows the growth in the number of transistors on a computer chip from 1971 to 2010. Notice that we used years since 1970 as the explanatory variable. If Moore's law is correct, then an exponential model should describe the relationship between the variables. Well, a scatter plot of the natural log, in this case log base E, or ln, of the number of transistors on a computer chip versus the years since 1970 is shown. So they take ln of the transistors versus the years since 1970, and you can see that this relationship looks a whole lot more linear. Whereas the previous graph, it looks rather exponential. In fact, it looks like it starts to grow really quickly right here, around 30 years since 1970, which would be around the year 2000. It really starts to shoot up really quick. So we take the natural log of the transistors, though, versus the years since 1970. So see, the x-axis hasn't changed at all. It's just the y-axis has now changed because it's ln of those numbers. That gives us this relationship looks a whole lot more linear. So based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between the number of transistors in years since 1970. Well, if an exponential model describes the relationship between two variables x and y, then we expect a scatter plot of x versus ln of y, x comma ln y, to be roughly linear. So we take the natural log, or any kind of log really, but we use natural log here for this example, of y. You will typically see them use ln or the log base 10. It doesn't really matter. You could do either one. I'm not sure if there's really an advantage to one versus the other. I think they both would do the same thing. It will obviously change what your y-axis is marked off as, but it won't really. It still should be a linear relationship. Anyways, the scatter plot of ln of transistors versus the years since 1970 has a fairly linear pattern, especially through the year 2000. So an exponential model seems reasonable here. Meaning tab output from a linear regression analysis on the transform data is shown below. Give the equation of the least squares regression line and be sure to define any variables you use. So for this, remember, the main thing that we need is the coefficients right here. The constant, that'll be your constant. This one will be the coefficient of your slope, your x basically. So what we have is ln of the transistors is equal to the constant, 7.0647, plus the coefficient of your slope, 0.36583, times your x variable, which is the years since 1970. So we've got our equation here. If we did ln of y and we used x right here, then we just need to define below what y and x are. That y is the number of transistors and x is the years since 1970. If you instead did that and not did words here. Alright, so we use this model to predict the number of transistors on an Intel computer chip in 2020. Show your work. So that's kind of interesting. So for last year, how many were there? So 2020 is 50 years since 1970. So we have ln of transistors equals, we basically plug in 50 for the years since 1970. When we solve that, we get 25.3562. And to find the number of transistors, we use the definition of a logarithm as an exponent. So this is base e. So we raise e to that power, 25.3562. And that comes out to be about 1.028 times 10 to the 11th. So the model predicts that an Intel chip made in 2020 will have about 100 billion transistors. Might be interesting to see what that actually is. I've not researched it, so you might want to take a moment and pause the video and maybe look to see what it is and see if Moore's law is holding true even to today. I'm not sure. Alright, so a residual plot of the linear regression in part B is shown to the left. Discuss what this graph tells you about the appropriateness of the model. Well, the residual plot shows a distinct pattern, with the residuals going from positive to positive as we move from left to right. But the residuals are small in size relative to the transform y values. Also, the scatter plot of the transform data is much more linear than the original scatter plot. We feel reasonably comfortable using this model to make predictions about the number of transistors on a computer chip. So even though it does kind of show a pattern here a little bit, the residuals are rather small relative, because you're talking about 1 and -1 here is what you're going from on the y-axis here on the residuals. How much off are they from the the predicted values off from the actual values. So they're relatively small residuals, so it should be fairly okay, especially since the scatter plot was pretty linear. If you go back to the scatter plot of the data right here, that is pretty linear. So if that's pretty linear, you can feel pretty confident regardless of the residual plot on using this model. So it's okay. All right. And then that brings us to the end. Hopefully this has been helpful. Hopefully you all have understood this stuff. With logarithms, I know that we've had to use a little bit more algebra in this section. I love it. But I know that that's had to bring up some background knowledge that we've had to access. And for some of you, if you had Algebra 2 in the COVID semester last year, this time, you may not have done logarithms. So I've had to teach you a little bit about logarithms. Please ask questions and let me know if you need extra help with those, because I will try to help you with those.